Yep, thanks, No. All right. So today we're going to move on to a different section or different types of machine learning approaches, kernels. So basically today and next Friday, we will be delving into kernels. It's a fun topic, and it's sort of a different sets of mathematical tools, slightly different sets of mathematical tools than what we have been dealing with. Yes, I do keyword search on XKCD on the topic that we're covering. As you can see, the word kernels and also margins for next Friday have many different meanings, as we will see soon. So before we do that, so assignment 2 is finished cooking and will be released very soon. So before end of this weekend, at least. So there are 3 big questions, base networks and EM, which you should be able to do after the graphical models content. So, but you're welcome to try. EM you have certainly seen. So kernel PCA is on content that we already covered, and you can already attempt already. And the autoencoder for recommender systems we covered in the neural networks 3 lecture. So that you should also be able to do. Needless to say, the suggestion is to start early. So the point breakdown also kind of reflects roughly how much work there is. I would personally say the base network one is probably more work, followed by the autoencoder, and the kernel PCA one is probably more straightforward, or like less number of questions. And there are bits where you deal with real data and bits that are open-ended, and I hope you enjoy tinkering with them. So next Monday, we wouldn't have a contact time. Instead, I offer to do a walkthrough of assignment 2 in this particular channel in the same format. People are welcome to join me or not. I will record a session. If you do join me, you can ask questions. If not, you can ask tutors later on. So that's that. So today's agenda is as follows. We've been talking about basis functions since the very beginning of this class. So we're going to start with a recap of that. We're going to then take a detour to what's called non-parametric methods, as you will, the relevance of which you will see. And then we will talk about dual representations of linear models, basically a representation that will allow us to work from the inner product space or kernel space. And then we talk about what are the general properties of kernels and how do you go about making kernels for your type of data anyway. What we will skirt or just not cover is the theory of reproducing kernel Hilbert space. For those of you who are very mathematically oriented, feel free to poke me for the reading, or go through those as additional entertainment. Next time, we're going to use kernels to build maximum margin classifiers. You may say that at the age of neural network, why do we care? There are very good reasons that you care in fact. So recent work on the theory behind neural networks are built on kernel machines. So here are basically what kernels mean according to Wikipedia. I have underlined in red the meanings that are related to what we cover in this class. In this particular lecture workshop, there are 2 senses. So this is chapter 2, covers the kernel in statistics as a weighing function, and then chapter 6 and 7 covers kernel methods, positive definite kernels, and reproducing kernel Hilbert space. So to refresh our memory, here's what we said about basis functions for classification. If we have a discriminant function that's linear with respect to input x, it looks like that, W transpose x plus the bias term. if we have a basis function phi that maps x to some other nonlinear space where phi is nonlinear. For example, in figure 4.12, phi is Gaussian with a fixed radius, then it will turn the nonlinearly separable red and blue points into linearly separable blobs in the phi space, indeed. So that's nice. Similar thing happens for regression. We've seen this particular picture a number of times. Figure 3.1 illustrates the different basis functions that we could use: polynomials, Gaussians, and sigmoids. So the forms of, so in this class, we call linear models linear because they're linear with respect to this basis function mapping phi of x. And also as a reminder, basis functions can represent nonlinear decision boundaries in the input space. And it separates class linearly in the feature space. So I'm underlying input and feature because these are, again, loaded terms in machine learning. In the context of the Bishop book, the input space is sometimes called feature in the wild, like when you talk about feature engineering from a real world task, such as like data dump from a bank or an internet company. So X is sometimes called features. And then, yes, and then in terms of features, right, so in deep learning, for example, there's talks about feature learning, and that meaning is consistent with what's used here, basically mapping from an input to some intermediate representation for that are then used for learning. And coming up with the feature itself is the process of learning again. So the good thing about basis functions, they can separate classes linearly in a feature space for classes that are not separable in the input space. So basis functions cannot remove class overlap that already exist in the input space. So it doesn't magically like reduce our base error rate and things like that. And if we look at basis functions in the format of phi of x, it needs to be pre-specified how many of them or what shapes of phi and hyperparameters. It cannot adapt its own shape to data, but neural net in a way can be seen as a way to adapt itself as basis functions, or the nonlinear activation function. And then, but neural network cannot adapt the number of features to data. So we have to specify the width or number of neurons in the neural network. So that's one of the things that kernels is promising to deliver, as we'll see today and next Friday. So the high-level ideas of where we're going is, instead of summarizing the training data into a set of weights with fixed lengths, we would like to ask the features to adapt to the data. Because of two intuitions. The first one is continuity. Most targets don't change, adapt abruptly. So we assume the mapping to the output in the input space is somewhat continuous and somewhat smooth, where here somewhat and smooth are very loosely interpreted. And then we also assume that the possible targets, input and target pairs that we haven't seen before is similar to the training data, needless to say. If these assumptions are broken, then of course the learning process as a whole is kind of broken. So kernels formalize these ideas in two different ways, right? So I would say, from the way I learned machine learning, the grouping of so-called non-parametric methods and kernels is sort of perhaps not common. It's also not a grouping that's used in the book, but it does make sense. And I think in order to pack like the different perspectives of machine learning approaches within the space of a mere 12 weeks or less. Yeah, let's just combine that part of chapter 2 and chapter 6 together. And there is a good reason to do that, right? So the three things we're going to talk about is histograms. Like you would have seen in, since whenever, since you first encountered data, maybe in high school or maybe in primary school, not sure. And how do we move from histogram to density estimation kernels and nearest neighbor classifiers? And then we're going to move on in the second half of this workshop to implicit feature mapping kernels. And in here, we talk about essentially two kinds of kernels. One kind is the one that we use to do smoothing and density estimation. They're also called Poisson windows. So they apply to histograms and simple density estimation kernels. And then the other sense we're using is basically positive semi-definite kernels that capture the similarity between data points. It computes an implicit feature map. The fact that it being implicit has many desirable features. So let's start from the first. Let's take a step back from classification and assume we are interested in observe density of data P of X given a set of observed X, right? So if we envision our X to be 1D and it's generated from this green density, like 2-mode density here, a natural way to do this is to say, oh, I'm just going to bin the input space and then count how many sample points fall into each bin. And that's an approximation of the histogram. So, right. Formally speaking, partition space into bins of width delta, count the number of points in each bin, and then normalize the estimates by computing P of I in the bin is the number of points in that bin divided by the total number of points. That will be the discrete, like this part will be the, say, the discretized probability measure. And then if we wanted to make it continuous, we divide by the bin width. As we can see that the estimate actually varies. So the estimate is piecewise constant within the bin. There is sort of for a particular density that we wanted to estimate, there is basically better or worse bin width. The bottom one is obviously too wide. The top one might be too narrow, so that it actually thinks there are like structures that weren't existing in the original distribution. So the pros for this histogram approach is that each data is used once. And then after that, once we have the bin boundaries, we can just look at the data, put it into a bin, increment the count, and discard it, right? The resulting estimate has fixed storage costs given bin widths. This matters as we talk about density estimation later. Right, so it doesn't matter whether we have 1,000 or 1,000,000 data points. We just need to store the maximum number of density numbers as number of bins, right? So it's also great for visualization. We can immediately eyeball the output and, for example, even see the bottom line is not really good. The cons of this is that, well, we need to somehow magically know what bin width to choose from. The usual rule of thumb is to not have too many data points in the bin, yet not have too few either, right? And there are discontinuities due to bin edges, which are just artificial. So if I have a point that's just slightly to the edge, left of the edge of the bin versus slightly to the right, it will contribute to just completely different bins. And this is statistically sort of not desirable. Furthermore, it does not work well in more than 2 dimensions. Basically, number of bins is exponential in the number of dimensions d, right? And it implicitly assumes there's a distance measure in some neighborhood that determines the bin membership of data points. So histograms are really simple, and it is still your go-to method if you want to understand your data once you first get it. Like pick the key dimension of the data in 1D or 2D, and then just histogram it. It's great, incredibly useful. But in order to move on and see a wider variety of methods and generalize from histogram, we're going to talk about kernel density estimates and nearest neighbor methods. So note that histogram bins are, let's say, rectangles, let's say in 2D, right? Let's first try and generalize these high dimensional rectangles or cubes. So if we assume we have n data points drawn ID from unknown distribution P of X in d-dimensional space, we can estimate the probability mass by just integrating the density function in this small region R, curly R. And the probability that k out of n data points fall within R follows a binomial distribution, as we've seen a while ago. So basically, n choose k of these points fall into the small region R with p raised to the power of k, and then this should be n minus k. N minus k points for outside of the region with probability 1 minus k, 1 minus p, right? So for a large n and sufficiently small region, we can say that maybe p of x is can be approximated as a constant. Assuming the volume of region R is V, then the big P is essentially P of X times the volume. And then we can kind of say that number of K is the fraction of points roughly that falls into the region R. And we kind of make a somewhat contradictory assumption that the volume is also sufficiently large that the number of points in there is non-trivial, right? And the binomial is sharply peaked or approaches Gaussian. So this will give the estimate little p of x at where the small region R is k over n times v. Okay, this may seem familiar because 2 slides earlier we kind of said, well, little p is ni over n times delta. So that's ni is k, and the being with delta is essentially the volume B. So we haven't changed the formula at all. And here we're just generalizing the notion of histogram to a small volume R and P of X in continuous space. So this simple scheme, including histograms, has the nice theoretical property that this density estimator and the kernel density estimator converge to the true probability density if we have n goes to infinite amount of data. If we have the volume V shrinks suitably with n. So here I'm not going into how suitably it is and what rate V should shrink, and K grows. So this is a result by Duda and Hart in the 1970s. So this gives us a number of things to play with, right? So assume we basically have a fixed n that goes to infinity or sufficiently large, then we can basically play with k. If we fix k, it will become what's called k nearest neighbors, either for density estimation or classification. If we fix v, then, but like make v not just a high dimensional cube, then this translates to kernel density estimates. So let's play with v first. As said, histograms are nothing but hypercubes, right? So within a cube where like the coordinate is less than a half on either side of the origin, the k of u is 1, otherwise it's outside of that, it's 0. And then the number of points is basically the indicator function, or this is the cube indicator function, sum over all data points of which data point falls into the cube. And p of x is basically the volume of the cube is h. Right, in here h is 1, like in the 2.247, but we could have cubes of different sizes. And then this term is obviously k summed over n. So this is essentially the same term, k over n times b. We haven't done like as this term on top. So we haven't improved from histograms yet. We just rewrote histogram in this more general form. So what is the sensible sort of density estimation kernel if we move beyond hypercubes then? We're familiar with Gaussians, right? So the desirables of these Poisson windows is that they are so sort of they are compact, so that their support region, or basically regions where they are non-zero, is suitably compact, and then it's hopefully it's monotonic with respect to, or decreasing with respect to distance to origin, right? Meaning, if I put a density estimation kernel somewhere, the points that are close to it contribute more in counts, and points far away contribute less. So the Gaussian kernel sort of satisfies this property. So we can intuitively think of it as a blurred version of the histogram, where the effect of beam boundaries is mitigated. So if 2 points that were lying just on either side of the beam boundary before, now they will have similar values according to the Gaussian kernel, right? So if we apply the Gaussian kernel to the same data set we've been looking at a few slides ago, we can see that, well, if we do have the choice of h, basically the width of the Gaussian kernel, if it's too narrow, it will just, the value of this will just be peaky around each individual data point. If it is too wide, then it will just over smooth the data point and sort of smear the probability mass induced by points to the far left to those on the far right. And the intermediate Gaussian windows seem to do a reasonably good job. So we haven't removed the drawback of having to choose a width for the estimation kernel. That's not going to go away, but we have removed the discontinuities of beam boundaries. And now we also have smooth estimates of the density, which is nice. So in general, if we choose any sensible KU, basically it needs to be positive and it needs to integrate to 1 so that the probability mass is preserved. We can just apply the same trick essentially to estimate densities. what we do, the recipe for doing this is simply to plug in the k function back into 2.249. Yep. So the advantage of this approach is, well, it's general, it doesn't have hard boundaries, produces nice looking estimates. What it does is we just need to store the training data. If we wanted to compute the density at the new some point that we haven't seen the training data, we just sum over the kernel value over all training points, right? So we don't need to sort of pre-compute anything. So that's a pro and also a con. So once we store all the training data, every single new estimate will take order of n time to evaluate, which can be undesirable. So that's when we fix V, but makes it the volume V, but make it something other than a high dimensional cube. Now let's look at fixing K, right? So basically, if we want, we consider local windows or local volumes where there's exactly K points falling into it. Suppose K is given, what happens, right? The criticism is that the kernel density estimate, the V is not adapting to the data. In other words, if I have a data that's far away, data point that's far away from everything else, it will kind of be lonely. And if I wanted to estimate densities where there has no, like the space is sparsely populated, will give me 0 or very close to 0. Right. Right. And we had to choose the width of the kernel H. So we know there's kind of no free lunch. If we now don't want to choose H, we must give up something else. But let's just try it, right, and see what is the trade-off. So if we fix K, we use the data to find the volume. So we consider a small sphere around X, around a data point, and then we allow the radius to grow until this little local sphere contains exactly K data points. And then we set V to the volume of the resulting sphere. So in one dimension, sphere is just a line segment, right? Centered on the data point. And this is what happened on the same data set. Note that it doesn't produce like proper density estimates, or it's rather jagged looking, but you can do this. And you can, right, okay. So it's hard to normalize this because if we envision, let's say, like on the real line, and if our point X is very far away from this these data, observed data, the V can be really, really big, right? So normalization is tricky. But what we can use these schemes for is, instead of doing density estimates, is it's very useful for classification. So again, we draw a sphere centered on the test data point containing precisely K points. And then we actually ask the K point to vote, right? Which point that this new point X, which class it should be in. So suppose we have K classes, so the we can compute the conditional probability using the density estimate idea of X given the class as the how many of these big K points belong to the small class, small k, over the total number of points in this small class divided by V. Same formula, same recipe. And then we can use Bayes' formula to compute the class posterior, which is then essentially simplifies into the fraction of the big K points that lies in this particular class. So that's very simple. Another nice property for this very simple scheme is that if we have infinite amount of data, the error rate of this one nearest neighbor, we aren't even voting, right? So for each test data point, we are just looking at its closest data point and then making it have the same label as that. The error rate of that is never more than twice the minimum achievable error rate of an optimal classifier. So if we knew the true class distribution versus we don't, the price we pay is with the one nearest neighbor is right only doubling the error. For some applications might be bad. For some, it might be actually quite good. For example, if you try one nearest neighbor on MNIST, it's probably not too crappy. And here's an illustration. Basically, for a new point, this black point, its closest neighbor is this red point, and then yeah, the nearest neighbor is approximated by like it will take the class label of this red point. I think this figure is missing something again. I don't have the print copy with me to check, but there, in order for the class discriminant or decision boundary between two classes for one nearest neighbor classifiers is always piecewise linear. You can actually show that. But in order for this figure to hold, there's got to be like other points that are red or blue on this particular picture. Yeah, you could actually, you show that by showing that for 2 points, one is red and one is blue, the one nearest neighbor decision boundary is essentially the line in between them. And if we just take the union of these lines of all point pairs, then we get the decision boundary, right? So that's that. So here's the example of one of the books often reused data sets, the oil flow data set. If we do nearest neighbor with k equals 1, indeed, the decision boundaries are piecewise like linear here. And we can see there are areas where the points of different classes pretty much overlap, right? Here, for example, red and green and so on. And this decision boundary is able to capture these fine granularities, right? Or these fine details. For example, there's a curly red region here. So you can see that the nearest neighbor classifier is quite expressive in terms of the shape of the decision boundaries, right? If we have higher values of k, let's say 3 or even 31, for the case of 3, the decision boundary is still kind of similar to k equals to 1, but then you can see that it's sort of has less details. K equals 31 has a boundaries or the regions for the classes that's almost unlike, especially for the red and green, they're almost unlike anything in the k equals 1 case. So this says that, okay, we don't have to choose V at this point, but choosing the k, the number of neighbors to vote on is very important. And if you use this, don't forget to do some cross-validation around the reasonable values of k. So that is what we wanted to say about what's called non-parametric methods. So it's called non-parametric. In machine learning, it has two meanings. One is there is no parameter, let's say, number of parameter that needs to be learned, where learn meaning minimizes some cost function, is 0. Of course, there are hyperparameters that just need to be set or chosen via cross-validation. So these like kernel density estimates and k nearest neighbor classifiers are these cases. And there's another sense of non-parametric methods, whereas the number of parameters is unbounded and potentially go to infinity, which we will not like outside of the scope of this class. So the examples of this kind of models include basically if we have a clustering algorithm, then the number of clusters sort of grows as the data arrives. So we have more and more data, or as the inference goes. There's something called the Chinese restaurant process for text or text-like data that is in this family. So we won't get to it in this class. Is there any questions so far?
Question that's kind of a slightly off topic, but
yep, go.
For k-nearest neighbors methods,
yep.
If you pick k to be a number that is less than every single data point you have, then as the data points that you use to predict a point shifts such that different data points get included, you have a discontinuity, right? There's a jump. So is there any way to get rid of that discontinuity?
I think that's a nice question. Let me first understand that we're talking about the same thing, right? Well, by discontinuity, you kind of mean this, right? So if I choose a fixed k and I move like my test point, which is where, for example, the laser pointer is in the space, and then the prediction sort of jumps at where the boundary is. Is that?
Yes, so the prediction jumps as you move your laser because a different point gets included in the prediction.
Yes. Yes, that's exactly what happens. Yes, and potentially multiple different points gets included in the prediction. This is exactly what happens, and it's desirable in this case, I would argue. Let me try arguing, see if you're convinced, is because we are talking about a classification task. So which class it is essentially a discrete prediction task, and we want it to change, right? So we are essentially learning. So, and another equivalent view of k-nearest neighbors is to actually learn these discriminant functions in the input space that are, say, don't have a parametric form, so to speak. And discriminant functions are kind of discontinuous objects, so to speak, because on one side it's one color, on the other side it's the other color, right? And the class label changes precisely because the underlying set of points change, because we are in k-nearest neighbor, we're doing this argmin, or the k closest points, and the prediction can only like take class labels of some of those points, right? We can't have the k-nearest neighbors being from class 1 and like red and green, and then the prediction come out to be blue. That would be just odd. Does that make sense? Does that explain?
Yeah, it makes sense, but I was just wondering if it's possible to use it for, I guess, continuous regression tasks where we don't want discontinuities.
Oh, yes, you can. You do this, right? Right. So if the kernel value, right, that's essentially what KDEs do. We can make basically, we can sort of use the idea from this picture. So if the regression function we're learning are something like the blue function, in here, we're just in here, we're having a density estimation plot, meaning assuming the value on each observed data points are the same. If we have a regression task, then what we're doing is essentially there is a function value that's sitting on each point as well, and then we do a weighted average of those points, function values. In fact, an idea that implements this is support vector regression. So as we will see next Friday, we essentially, for all our data points, we kind of pick which points as support vectors, and then we do a weighted average of their their regression values too, the Y output. Yeah, you feel free to skip ahead to section 7 or hold off for a week. If
Okay.
that, yeah.
Thanks.
Cheers. If everybody else is happy, then we're gonna move on to a bit more linear algebra. Or actually, we haven't done linear algebra this today, so we're gonna do that. If not, feel free to interrupt me. And there's a few more talking slides here. So what is the role of training data in here? Like in the regression and classification section, or even in Gaussian mixtures, we were saying, oh, the role of training data is to get summarized into a set of weights or model parameters, such as means and variances, right? But for in here, what's called non-parametric method, like we're just remembering the training data, right? And then using perform inference or prediction on top of on them. What in kernel methods, what we do is to use training data in a way that we compute kernel functions at a subset of training data and then use them to do prediction one way or the other. We talked about input space versus feature space. I think it's just to be nice to be crystal clear whenever we talk about them. And it's also this term is also inconsistent in the community or even in different sections of this class. So we when we write out, like when I specify the exam questions and when you write the answers, make sure you're being clear. I think that is that's right, a sane approach. For example, the original data or the input data are sometimes called raw features. Yes, you can't. Yeah, you can call them features, raw features, or input. And then the feature space can be called derived features. There are a whole subfield of machine learning called feature selection, which are practically quite relevant because when you work for a bank, you don't want to go tell your boss, look, I built this predictor on 1 million user features, and here's the outcome. And you can't audit which features are useful or which input is useful. And in that sense, a lot of these literature refer to the input selection. And then feature extraction can refer to the process of us tinkering with the database and coming up with the input, or like having parts of our deep neural network learn what's called features. Again, so features and input all serve as they serve as various purposes. Like we want a representation that's informative to the target, that are compact, or we want them to be explainable to humans. Right, so terminology warning in short. So before we dive into the linear algebra, so here is the kernel method in one slide. Here is the outcome we aim to get, in short, in this session and also next week. And the difference of which I can tell you a bit later. So if we have a set of learned training data, xi, ti's, which is familiar to us. On the new point x, instead of doing y of x equals w transpose x or w transpose of phi x, right, I'm just gonna write out the, like, instead of doing this, now we do basically alpha I, a different set of weights, alpha I or AI are just weights, times this kernel function. As we said, we're now remembering the training points, right? K is a kernel function that computes intuitively the similarity between the test point and some training points. Okay, so this is something new, but the format is still somewhat similar. Right. So in other words, this connects to what we talked about in kernel density estimate and so on. The prediction is a weighted average of the training targets. Or Ella, if you can take this as, for example, one of the answers to your question, yes, you can do this, right? Prediction is the weighted average of the training targets, and the kernel function is usually smooth, continuous. A lot of them are, not all of them are. And the weights depend on the similarity of x to each training example. Okay, so the weights are what we learn for things like support vector machines. So here is another familiar picture of what like a training objective would be. So this is the, say, ridge regression objective that we encountered many, many times. If our y equals w transpose of phi of x, and we observe training target TNs, this is the sum of square error on the training data, plus a regularization term for the weights, because we don't want the weights to explode. We have also repeatedly written this back into matrix form, right? So we write these 5 functions as a matrix. So by now you're very familiar. I guess this is the first dimension, first feature function or feature kernel, and then the rows are basically phi x and transpose. So this is a data point, right? So therefore we have big N rows and then M columns. So we also know from the normal equation on the regression section that the solution to this is this linear algebra expression. So the inverse of this regularization term introduces lambda I, and the regression term basically is the pseudo inverse phi transpose phi, taking the inverse times phi transpose t. All right. And the prediction function is phi, essentially w transpose phi or phi transpose w, because these are vectors. Vector inner products, it doesn't really matter which one we write first. In here, w star is the complicated quantity, so it's handy to not having to transpose this whole thing involving the inverse. Therefore, we can just plug in the expression above and just write the prediction is the inner product between the feature vector of the test point and this whole thing, right? That's W. Okay, we don't need this slide. I will delete this. So where are we going with this, right? So our goal here, let's say, our goal for this next few slides is to go from this phi representation to kernels of 2 variables. All right. So this slide looks busy, but the new content is not that much. This phi matrix I'm just putting it here for reference. This is the same objective function or loss function for ridge regression. This is the ridge regression loss function written in matrix form. we can easily verify. By now, we should be familiar with this. If we have a sum of squares, we can rewrite it as the quadratic form involving the corresponding like vector differences, right? And the regularization term is already an inner product form. And this we also saw on the last slide. Now what we do is we move around terms a little bit, right? Obviously, we take W star, the optimal W, and just multiply. So instead of dealing with the inverse, we multiply this matrix in the normal equation on both sides, multiply this on both sides. So on the right-hand side, we are left with phi transpose T. On the left-hand side, we're left with this thing, right? Phi transpose phi plus lambda I times W, which is like this is matrix. And now what we do is we notice that lambda I times W is lambda W, right? I times the vector is still the vector itself. And then we move everything else to the other side. And here we cheat a little bit, right? So the right-hand side still has W here, but let's say we don't care. And we rearrange terms, right? So we move the phi transpose phi W to the other side, and then we just group everything here and call it A. So how did people come up with this? I suspect it's post hoc. Well, in the book context of this book is post hoc. Like we kind of know the answer and work backwards. But for now, let's say we have now expressed W as the linear combination of phi, where the weights kind of involve W itself, but we'll deal with that later, right? So this is the key message here. Basically, what it says is the solution to the linear regression problem is a linear regression to the features of each input, right? And now we plug this back into the loss function J. We stare at this. Basically, we first expand the quadratic term in J. Like the half of T transpose T term is fixed. And whenever we see W, so the quadratic term regarding W will now, so W would get turned to phi transpose alpha. And the quadratic term of W, basically, this term will turn into this. And then the linear term of W will turn into, actually my, will turn, right. So the regularizer term turn into this. And yeah, W squared, more or less, W squared times phi turn into this first term, and then the linear term turns into this. All right, so we just took the loss function J of W and made it a lot longer. What have we gained, right? Remember our goal. So what we do is now we define, so we now notice that the feature matrix phi appears in pairs always, right? They're here, they're here, they're here, right? And the pair is basically phi transpose or phi transpose phi. So we want the feature matrix to be an n, or the kernel matrix to be an n by n matrix that encodes the similarity between each pair of training data points. So we define k equals phi transpose. As you will see, you have seen in the PCA lecture and also the kernel PCA assignment, you could define another matrix, basically phi transpose phi. So this will be an m by m matrix, right? So there are relationships between this K matrix and this of like phi transpose phi, which is sort of covariance matrix for if phi is centered. Phi is not centered, then it's not exactly the covariance. Right. So for now, because we've been talking about remembering the data point, we want this matrix to be n by n. So we do this kernel K in this particular way, not the other way. And if we are more comfortable with sort of defining a matrix by its elements, each element, you can go and verify using the matrix phi, is basically the inner product of the nth feature versus, the feature of the nth data point is small m's data point, right? So this also says, also because of this definition, the big matrix K or inner product matrix K is symmetric. And so we do this, and now we can rewrite the loss function in terms of K. It's still a long expression, but it's much shorter now. So there is now there is only one quadratic term of K, and then two linear term of K, and then one constant term with respect to K, right? So we like quadratic expressions. We just made, for example, the loss function more complicated to have like fourth order terms in terms of the features. Now we make it back to a quadratic term. So we also know that we can solve quadratic forms of matrices to get their local minimums. We've done this enough times. I guess we don't need to do this in real time. So the minimum, right? So if we minimize J of A with respect to H, the minimizer is A equals K plus lambda I inverse times T. We could mentally verify this by applying like the way I do it is I now pretend the symbols are scalars, and then I'm trying to use the high school like quadratic form formula to verify it. And that's sensible, basically. The twice, like the linear, the linear coefficients over twice the quadratic coefficients, which is this. And there are two quadratic terms with respect to A now, right? So, which is the group of this and this on the denominator. All right, given this, now we have A. We plug it in back to the original predictor y equals w transpose phi of x. Yes, we have expressed A, which were not independent or which involved w at the beginning, but here the solution did not involve w, right? So the k is determined by input data, the other things are all determined by input data. Lambda is a hyperparameter, right? So now we can just plug back in by substituting w equals A transpose phi. Notice now we're multiplying the big phi matrix with the feature function of the test point, little phi of x. So the desirable qualities we want is we wanted to avoid computing the phi for reasons we will cover this time and the next time. So we want to avoid computing phi explicitly. And we want everything to be like kernel K. So what these two terms turns into is essentially the kx term, where kx is essentially the kernel value as a vector. It's a kernel value between the test point x and every single training point xn. And then times this alpha vector or a vector that we solved before. So a few slides ago, we had this prediction function. What this term does is essentially regroup, right? So as we can, the connection between this solution is that phi transpose phi turn into k, right? This inverse term is essentially the same. And then, right. So if we regroup, well, with some linear algebra, this phi transpose and then the test kernel feature, test feature phi x, we get this kernel vector kx here. All right. Okay, so we kind of delivered what we wanted to, what we said we will do, like in the kernel method in one slide. The advantage here is solving for A is kind of easy. It just involves a matrix inverse. The disadvantage is also that it involved a matrix inverse that's n by n, right? We know that matrix inverse is sort of an order of n cubed operation, so this can get quite expensive. And furthermore, we're just remembering our training points, right, with this kernel matrix big K. We wonder if we can do better than that, and that's what the max margin classifier will do next week. But for now, we're going to sort of take the discussion in a slightly different direction and talk about what are these kernels and how do we construct kernels and why do we not want to compute phi? Is there any questions? Nope. Just gonna move on. The kernel function defined on 2 points, again, looks like this. Phi transpose phi. And then if we can compute phi over its m dimensions, it's sum over each of the m dimensions pair, like element-wise product, right? So this is obviously symmetric. It's an inner product of two vectors of basis functions. And we already said the at prediction time it will be evaluated at the training data points. Right. An example of this, so we talked about polynomial kernels a lot. And they are simpler, they are like one of the simpler kernels, right? If we take this definition of kernels and say, oh, if we want the kernel function to be this, essentially the inner product of two, like the second order thing, like quadratic term of the inner product of two vectors. And if we assume that each of these vectors are two-dimensional, we can expand them as follows, right? The inner product expands into x1, z1 plus x1, x2, z2 squared. And if we expand the square, we get the cross term and the quadratic term. So how do we now make these into like the form of phi? The way to do this is, and furthermore, the one phi term needs to include, right? So here there are three terms now, which are the resulting result of an inner product. And we want one of the phi's to only involve x's, the other one of the phi's to only involve the z's. So basically for each of these terms, we like tear apart the x terms and the z terms and put them into corresponding elements. And moreover, we need the mapping to x and for x and z to be exactly the same, and that determines this square root of 2 term in the middle. Right, when the coefficient is 1, it's easy. So when the coefficient is not 1, we need to take its square root. So therefore, phi of x is x1 squared, square root of 2, x1, x2, and x2 squared. Right, so you can argue this is the sort of a simplest quadratic kernel we can get. And the phi of x is sort of slightly more complicated looking than the k already. And that's one motivation to work in the space of the k rather than the phi's. In general, right, more generally, we don't want to be doing this sort of eyeballing the expression and tearing apart the phi's all the time. So it's a good exercise, right? And you will get to do this in kernel PCA homework, right? Do this for cubic kernels. Yeah, so construct cubic right, basis functions in like question 2 of assignment 1. Assignment 2, okay. More generally, we're lazy, we want convenience. So we wanted to be able to write out a kernel function, any function, and then assert whether or not there exists a set of basis vectors, the basis functions phi, so that it's a valid kernel function, right? So there are results from reproducing kernel Hilbert spaces that support this kind of reasoning, right? So unnecessary, the nice result says, insufficient condition for a function kxx prime to be a valid kernel. This is summarized in the textbook by Sean Taylor and Cristiani, is that the gram matrix K, whose elements are given by K of x and xm, should be positive semi-definite for all possible choices of training data. Right, basically, it's given K is already a symmetric matrix, its eigenvalues are real, and eigenvectors are all real, assuming the kernel values are real. Well, complex kernels is you can have complex kernels, but let's say for the sake of this class and our sanity, we just stay away from them for for the time being. So let's say if we have K real, then basically any, well, K for any training data set or any data set should be positive semi-definite, right? So K of any data set or its subset is should be greater or equal to 0. All the eigenvalues should be greater or equal to 0. So right, you can say, well, any super power sets or subsets of data points X, that can be hard to directly validate too. So here is a recipe for practitioners, right? We will cover that in 2 slides, which is basically build kernels out of known kernels. But before that, let's establish some intuition about this kernel function or similarity function. So as we saw throughout this class, these are kind of functions phi that we often see, right? Polynomials of different order, Gaussians or radial basis functions, and sigmoids. Sigmoids are not actually valid kernels, but let's say, and the k function, if we center over x prime equals to 0, all look kind of similar. Despite the original function don't look similar, but the kernel function have this similar shape. It has a bump around 0, and then it oscillates a little bit, right? Note that in the last slide, there was this note saying being positive definite, it's not the same thing as a matrix whose elements are non-negative. Basically, elements of the kernel can indeed be negative. So as reflected here, so it can have negative values. Right. So here's the practical recipe for constructing new kernels if you don't want to go and prove that a particular kernel function defines valid RKHS. Basically, if we have a valid kernel, if we have a valid kernel K1, then and if we multiply it by a positive constant, it's still a valid kernel, right? And moreover, like due to this fact here, if we have two valid kernels, we can sum them up and form a valid kernel. The combination of these two basically says any linear combination of valid kernels is still a valid kernel. Similarly, we can compose kernels by function composition, right? So this is polynomials, right? Polynomials of existing kernels, exponentials of existing kernels, products of existing kernels. As you can see, these, like if we're given polynomial kernel and Gaussian kernels, these constructs allows us to do quite a number of things already, right? And if we have a basis function, then kernel of the basis vectors is also a valid kernel. Moreover, if we have a symmetric positive definite matrix already, we can use that to construct a kernel, right, in here. And if we have kernels operating on subspaces, right, of X, then compositions, let's say sum products of those kernels, are also valid kernels, as said here, right? So a set of simple tricks to help us construct kernels. An example of that, like as an application of what we just said, let's verify that the Gaussian or RBF kernel is a kernel, right? So the Gaussian function has the form of basically exp exponentiating a quadratic function of x. The constant in front don't matter because what we said here of a constant times a valid kernel is still a valid kernel, right? So we just consider this form. We first look at the stuff inside. The quadratic form itself can be basically paired apart into x transpose x, x prime transpose itself, or and then the cross term, right? So and then the exponentiation applies to the three terms respectively. So we can see for the last bit, for example, exponentiating, so linear kernels, or basically inner products of vectors itself, is a valid kernel, right, in here. We exponentiate that because of what's on the last page, that's a valid kernel. The exponentiation of that only involves x or x prime are not part of the kernel function because they're not functions of the two variables, right? So therefore the RBF kernel is a valid kernel function. further examples of kernels, you can, this is left as exercise. We can do not only quadratics, but m's order exponentiation of the inner product, or inner product plus a constant. Yeah, and sigmoid kernel is not valid. And generally we call basically kernels that involve the inner products only linear kernel, right? Kernels that only depend on, let's say, the difference of the vectors, stationary kernels. Basically, the kernel value does not depend on where x and x prime sit exactly, but it only depends on their distance. Homogeneous kernels take this further. It's only depends on the absolute, like the norm of the difference between the two vectors. And does not depend on the direction. So the latter two kind is quite widely used in Gaussian processes, which we're not going to talk about in this class. This little bit goes slightly beyond the book, but I think it's good to know for cultural reasons. Meaning that if you have data that are not just numbers, but say graphs, sets, strings, such as text or DNA sequences or things like that. How do we construct a kernel for that? So basically, if we have a discrete set, curly A, and we can denote the power set of A as P of A, and if we have two subsets of A, we can, let's say, compute the cardinality of the intersection of these two power sets and exponentiate that. So that will lead to a valid kernel function. So that's rather handy. And we can generalize this notion to basically this notion directly lead to what's called n-gram kernels, or if you work with biological sequences, k-mers, right? If we take all the lengths to, say, substring of a DNA string or a text, and we take their intersection, basically we're counting, say, length 2 or bigrams on the text, and that will, and exponentiate that will lead to a valid kernel. In fact, this is what like the early applications to biological sequence classification, besides hidden Markov models, which we'll talk about towards the end of the semester, is kernel methods and string kernels. And moreover, there are scenarios where we can estimate probabilistic models out of our data, P of X. We can compare, so the probabilistic model we estimate contains useful summaries of the data. So we would like to compute the similarity of two observations sort of conditioned on the probabilistic model, or that are as projected onto the probability model. And here's the way to do this, right? So if we have a weighing function P of I, where I is discrete, or P of Z, and Z is continuous, think of, say, mixture components in Gaussian mixture models, or, well, HMMs in continuous space, which we will talk about. Then we can compute essentially the kernel function as like essentially the inner product of the data likelihood in these individual model space. So far what we have talked about is we want to pick a suitable kernel function that computes inner product of some basis, implicitly some basis functions, or the similarity between data points. When it says implicitly, one example of phi of x that we cannot get easily is the Gaussian or RBF kernel. You can feel free to go verify or try and pull it apart. It's hard. So we can then make predictions by combining kernel, the functions, the values of these similarities to training data, right? So it's implicitly a linear model in some high dimensional space and potentially infinite dimensional space. One way to view the RBF function is that we can, as with any continuous function, we can do the Taylor expansion and verify that the coefficients on high order polynomials don't vanish, right? So therefore, that we could view that as an infinite dimensional space. So for linear regression, we go from this expression that involves phi to essentially this expression that involves the kernel function only. So basically, as we can plug and play phi, we can plug and play kernel function. The advantage of working in the kernel function space is the dimensionality of this don't change, right? If we change from, let's say, the second order polynomial, which are like maybe in the three-dimensional basis function space versus the fourth order, maybe that will be in a much larger basis function space. The dimensionality of the kernel space is always n by n. Could still be big, but it doesn't change. That's a nice thing about it. So that's basically what we want and need to cover. The next session, we're going to talk about basically better ways of constructing this function on picking training data. And we will take an optimization view. Basically, we will extensively use Lagrange multipliers. So that's all for today. Is there any questions? Nope. Everybody happy? I'm just gonna stop the recording.